In this video, we're going to look at the existence and uniqueness of ODE, ordinary differential equation, solutions. First, we're going to determine if the first order differential equation has a unique solution, and then we're going to determine if the solution to the first order differential equation, if solutions, more than one, actually intersect. So we're going to start out with a nice warm-up. Find the function or functions family of functions that satisfy the differential equation y prime is equal to negative y squared over x squared, where the initial conditions of y of 0 is equal to 1, y of 0 is equal to 0, and y of 1 is equal to 1. Now, if we take a look at this original problem here, this y prime is equal to negative x squared or negative y squared over x squared. We happen to know this is a separable differential equation, so we're going to treat it as such. We're going to divide both sides by y squared. And in fact, I'm probably going to divide both sides by negative y squared. No real particular reason. I mean, I could totally not, but in this case I will, because you'll see when I integrate it why I'd want to do that. So I have negative 1 over y squared, y prime, is equal to 1 over x squared. And I'm just going to rewrite this as negative 1 over y squared dy dx is equal to 1 over x squared. So I have negative 1 over y squared dy is equal to 1 over x squared dx. Now let's go ahead and integrate this. So we're going to integrate negative 1 over y squared dy is the integration of 1 over x dx. And then don't forget the plus c. When we integrate the left-hand side, we're going to get 1 over y. And this is why I kept a negative with the y, is because when I integrate this, remember this is the same thing as y raised to the negative 1. I add a power, divide by that negative 1, and this allows me to have on the left-hand side a positive 1 over y for no real reason. It just is a little nicer, but not necessary, by the way. Over on the other side, I'm going to get negative 1 over x plus c. So in other words, when I solve for y, I'm going to get y is equal to x over cx minus 1. All I did was I multiplied everything by xy and then solved for y. Now with the initial condition, we'll start with the first initial condition. When we have x as being 0, this is my first initial condition, x is 0, y is 1. Then I'm going to come over here, and when I do have the initial condition of y of 0 is equal to 1, and I plug in that information into this equation, so I've got 1 is equal to 0 over 0 minus 1, and this is y is equal to 0, or excuse me, 1 is equal to 0. That's never going to happen. So there is no solution for this initial value. So there is no solution for the initial value of y equals 0, or y equals 1 and x is equal to 0. So y of 0 is equal to 1. The second initial condition I have is y of 0 is equal to 0. So again, I'm going to put it into this equation right here. And I get 0 is equal to 0 over 0 minus 1, and this is a true statement, so I get 0 is equal to 0. So that tells me that c is equal to 0, so c is equal to 0. And because remember that it's 0 times c here, just like this was 0 times c here, so c has to equal 0. So the equation that I get with that initial value is y is equal to x over 0 minus 1, or in other words, negative x. So that satisfies that solution. My third and final solution is initial condition, the initial condition was, I believe it was y equals 1. Let me go back over here. When y equals 1 and x is equal to 1, so y of 1 is equal to 1. So I have 1 is equal to 1 over c multiplied by 1 minus 1. When I solve for this, I get c is equal to 2, so I have y is equal to x over 2x minus 1. Now, this obviously has no solution. This initial value has a no solution. With this given initial value, we actually have an infinite number of solutions. There's an infinite number of x's that you could put in to get a value for y. This one has a unique solution. So we have 3 different cases for the same differential equation based on the initial value. No solution, infinite number of solutions, and a unique solution. So let's go over here and say, hey, what does this all mean? First order differential equations that take on the form y prime is equal to f of tx, or you might see this as y prime is equal to f of x comma y, where I have this initial condition. In this case, I'm using x's and t's. So x of t naught is equal to x naught. It can be solved only in very special cases. We have looked at some of these cases I'm going to list, and some of them we're going to be looking at. We have the linear equations, which we did in 2.3. We had separable equations, which we did in the beginning of the chapter. We're going to do Bernoulli equations, which is the next section. Then we're also going to look at homogeneous equations and geometric approximations. Those are the direction fields, and we're going to look at those at the end of this chapter. It's important to note that there is no method for solving the equation of f prime or y prime is equal to a function of t and x in general. Now we also need to determine whether or not there is more than one solution, like we did in our warm-up, passing through the initial conditions. So first we're going to start out with me erasing this, because for whatever reason it's locked, but none of the rest of it is, so I'll just have to erase that. My apologies for that moment of erasure. We're going to start with the theorem of uniqueness and the existence. So if we have some differential equation, and again, I'm using x primes, but you can use y primes and just use x and y instead of t and x. If the function is defined and continuous everywhere inside some given rectangle where I have values for my t and values for my x in the tx plane, and it contains some initial point t naught, x naught, it's an interior. So in other words, I'm not looking at the edges of this rectangle. I'm looking only inside this rectangle. Then there exists a solution x of t passing through this initial condition or this initial point, and the solution is continuous on that interval where I have t naught minus epsilon t, which is less than t naught plus epsilon for some epsilon. If the partial derivative of f with respect to x is continuous in R, then there exists exactly one solution. That is, the solution is unique. Now, if you remember, this looks a lot like what we would expect in calculus. If you take a continuous functions class, or continuous functions class or real analysis, you will delve even deeper into this, but we're just kind of touching on it lightly. This theorem that we have doesn't actually imply the solutions exist for all t, even if the function is differentiable. Now going back to our example that we had, which was f of xy is equal to negative y squared over x squared, it is not continuous on any rectangle that contains the x being 0. So any rectangle where the x is 0, so if I choose this rectangle that is right here at the origin, and I go rectangle from negative 1 to 1 in the x direction and 1 to 1 in the y direction, this rectangle here will not be continuous. And that's because it is negative y squared over x squared, and if x was equal to 0, then obviously it's undefined. So the existence and uniqueness theorem I just had does not actually apply to any case in which I have an initial condition of y naught, or y of 0 is equal to 1, and also for y of 0 is equal to 0. The theorem does apply for that case where I had y of 1 is equal to 1. So these two cases in which I started out with for my first case, which was y of 0 is equal to 0 and y of 0 is equal to 1, this one didn't exist. This solution didn't exist, and this one had an infinite number of solutions. And that's because of the fact that if I were to include any rectangle that had an x part being 0, it's actually not continuous. So you can see by looking at our slope field, if I go from negative 3 to 3 and negative 3 to 3 both in the x and the y direction, that I don't have any slopes on my slope field on the x or on the y axis, and also at the origin. So we're now going to define a Lipschitz condition. And you're like, yeah, it made me giggle too a little bit the first time. Okay, I'm a little childish at times. A function f of t is defined on a bounded rectangular region, that means we get to include the edges, is said to satisfy the Lipschitz condition on R if for any 2 points, tx1 and tx2, in that rectangle, there exists a positive constant m such that the absolute value of that function evaluated at x1, x2 outputs, have at t with x1, x2 outputs, is less than or equal to some positive constant m multiplied by the absolute value of x2 minus x1. Now we want to note that the partial derivative of f with respect to x does exist and is continuous in R. Then we can use the maximum value of that in R as a Lipschitz constant for m. So if we go back to x prime is equal to a function of t comma x, and we're given the initial condition of x of t naught y naught, we know the solution to that will take on the form of x of t is equal to x naught plus from t naught to t of f of s, x of s ds. Now we can solve this with an iterative process, and we end up with this limit. The limit as n goes to infinity of t naught to t of f of s, x sub n, s, d of s, is going to be equal to, by the fact that we can use limit laws, the t to 0, the integration from t naught to t of f of s, the limit of the function of x sub n, s, ds. And then we would require a theorem called the Monotone Convergence theorem for integrals, and this in and of itself can be pretty difficult. Now, if you look at your book, if you open up your book and look at example 2.4.1, the book goes through a pretty good example of this iterative process, and I'm not going to go through it here. We also get this other lemma that is let x prime equal to f of tx be the first order differential equation with f, the function, and its partial derivative with respect to x, both continuous on the values of t and x in some region in this plane. Then inside the region R, the solution curves of differential equations will form the non-intersecting space filling family of curves. In other words, it will fill the entire space. So here's an example. Determine if the differential equation has a unique solution through every point x naught, y naught. Will the solutions of curves intersect? All right. So first of all, we know that x squared 1 plus t squared, which is the f of tx. And let's do its partial derivative with respect to x. So our partial derivative with respect to x, which will equal 2x over 1 plus t squared, are both continuous for all the values of t and x. Therefore, the solution has a unique solution for every single point in the x or t naught, x naught. And the solutions cannot intersect anywhere in the plane because they're unique. If they're unique, they are not going to intersect. So let's determine if, on my next example, determine if the differential equation x prime is equal to x of t, the quantity squared minus t, has unique solutions in every point. Will the solution of curves intersect? So our function, f of t of x, is x squared minus t. And my partial derivative with respect to x of this function is 2x. These are both continuous for all t and x. There's no parts of discontinuity. There's no division by 0. Then we know that the solutions will be unique through any initial point, and the solutions will never intersect. Now, if you're thinking, okay, what's the difference between these two? How do I know they're both true? Well, let's just talk about these right here. The problem child is always the denominator when you have functions in which I have a function divided by a function, a rational function. It's not necessarily rational, but a function divided by a function. They don't have to be polynomials. So anyways, we know that no matter what we put in for t, we're never going to get 0 because I have a positive plus a positive will always be positive. Even if that is 0, if t is 0, I still have 1 in the denominator, and that's how come I have no restrictions. So both of those. Let's take a look at my third example. Draw a slope field for the equation y prime is equal to x raised to the 2/3 in the rectangular region between -3 and 3 for the t and -3 and 3 for the x. Will the curves ever intersect, and if so, where? So we have this first part, the f of t of x is x raised to the 2/3, and that's just the cube root of x, the quantity squared. Totally cool. That's defined everywhere. Now, when I do its partial derivative with respect to x, this is going to be 2/3 x raised to the -1/3. Now, the problem with this one is that when x is equal to 0, the partial derivative with respect to x is not defined. So the theorem does not apply. So anytime this theorem does not apply, then we know that we can't say that they're going to be unique, and we can't say that they aren't going to cross each other. Now, let's go through the process, and we say my d of x over d, not partial, d of t is equal to x raised to the 2/3, because that's what this is saying. And this is a nice integral. This is separable. I would write this as x raised to the 2/3 dx is equal to 1 dt. The integration of x raised to the 2/3 dx is equal to the integral of dt plus c. And I'm going to end up with 3x raised to the 1/3 is equal to t plus c. And so I have x of t as a function is equal to t plus c over 3 cubed. So that's my function. It has a solution through 0, 0. So when I go through x of 0 is equal to 0, this will take on x of t, which will equal to t over 3 raised to the 3rd. And this is just a solution when x of t is equal to 0. This is just an option. There are other points in which this 0 of 0 will be satisfied. If I go back to my slope field end up, again, if you need a moment to remind our slope field, is we put in the ordered pairs 0, 0 or 1, 1, and we build our slope field from there. And remember, our x prime is equal to x raised to the 2/3. This is totally dependent on x. That means there's no dependent on this in terms of t. So remember, when we're doing slope fields, if that happens, then it's a copy and paste left and right. So all I really have to do then is I have to put in when x is equal to 1, I'm going to get x prime, which is going to equal to 1. When x is equal to -1, x prime will also equal 1. And that's because I have the x quantity squared, and then I take the cube root of it. So I know when x is equal to 1, I have the slope of 1 all the way across, left to right, like this. And the same thing when x is equal to 1, I have this slope field left, or not left and right. I don't know why I'm going up and down. I was saying left and right, I was going up and down. So left and right will have the same slope field. And of course, in your mind's eye, you're making these look really nice, all with a slope of 1 and going in that direction. So then I would put in when x is equal to 2, x prime is going to be the cube root of 4. And then I would get that slope. And so I would do the next one, which is a little bit higher, and I go left and right. And I would go in the other direction. And that's how, as you remember, filling out the slope field. And with the magic of Desmos, here is the slope field filled out for us. And this is what it looks like. Let's take a look at my next example. Let's take that over there. I don't know why it doesn't want to. There we go. Let's move that out of there too. So we're given this slope field for the differential equations y prime is equal to x, 2xy, where the initial condition of y of 0 is equal to 1, with a slope field in the rectangle of negative 1.5 to 3 for x and negative 1 to 8 for the y. Does the solution have a unique solution from every single initial point, and will the solution of curves ever intersect? So again, we're going to see if our function f of xy, which is equal to 2xy, that is continuous everywhere, and this partial derivative with respect to y is equal to 2x, and that's continuous everywhere. So yes, it will be continuous, it will be unique, and no, they will never intersect. So then we're going to use the directional field to sketch the solution curve that satisfies the initial condition. So I go to the point 0 for the x and 1 for the y, which is right here, 0 for the x and 1 for the y. And then I'm going to follow through with that initial condition. I'm going to follow through by following these slope field lines. And you can see as I'm starting to sketch it, it looks like it's looking like something like this. So all I do is I just follow along on the line where it looks like it seems to be going through, and this is what it kind of looks like. It looks something like that. So if I want to find the exact solution, we know that this particular function, f of xy, is linear. So we need to find our integrating factor. So I'm going to rewrite the function in the way that I'm more familiar with, and so that would be y prime minus 2xy plus is equal to 0. So it's a homogeneous linear. And so I have my integrating factor, which will be e raised to the negative 2x dx. Because remember, we need it to be in y prime plus my function of x, so we'll call it p of x, y is equal to g of x, and so it has to be a plus, so it's a negative 2x. My integrating factor then is e raised to the negative x squared, so there's my integrating factor. So then what I have is I have y is equal to 1 over e raised to the negative x squared, the integration of, well, this is going to be 0 dx plus c. Well, the integration of 0 must have meant that I started out with a constant there. So the only way that happens, oh, don't forget my parentheses there. So what I have is 1 over e raised to the negative x squared. And I have a constant, I'm going to call this one a constant 1 plus this other constant, which means what I really have, and I'm going to add these together, and I'm going to just say, well, that's just a constant. A constant plus a constant is just a constant. So then this is equal to e raised to the positive x squared because of negative exponents multiplied by my constant c. So what I have is y is equal to c e raised to the x squared. Now my initial condition, which was 0, I believe my initial condition was 0, 1. So I need to have 0 is equal to 1. That means 1 is equal to c e raised to the 0. That means c is equal to 1. Therefore, my equation is y is equal to e raised to the x squared. And if I were to graph e raised to the x squared, it should look something like this blue curve that I did up above. And that's it for this video.